Hello everyone, my name is Al-Habashna. I'm a postdoctoral fellow at the Systems and Computer Engineering Department at Carleton University. Today with my colleagues Vinu, Rajus and Nicolas Arellano are going to present our work which is about indoor localization and building occupancy count estimation using LTE advanced ultra-dense networks. We propose an approach for indoor localization using LTE advanced ultra-dense networks. We also detail how accurate localization and occupancy count estimation can be used in studying and analysis of two important building-related aspects. These are studying building occupants' behavior and model their personas, and also using the data provided by the localization method in BIM models for visualization purposes. New network architectures such as ultra-dense networks and ultra-dense heterogeneous networks are enabling technologies to meet the increasing demands and achieve the required performance of 5G cellular networks. With the ultra-dense networks, the density of the operator-based and the user-deployed elements are increased, improving coverage, frequency reuse, and achieving higher data rates for cellular networks. In ultra-dense HetNets, several types of wireless access nodes are employed, and hence macro cells are overlaid with low-power nodes such as remote radio heads and pico cells. These smaller cells can be used to offload traffic, which improves the network coverage at the cell edge and increase data rates. The LTE Advanced Pro standard proposes different scenarios for implementation of ultra-dense networks and ultra-dense heterogeneous networks. These include scenarios for homogeneous ultra-dense networks where similar elements are employed, such as picocells, and also scenarios for heterogeneous networks where distinct or different types of cells coexist. We are interested in scenario A, shown here because our work is focused on indoor localization and building occupancy count estimation. Each antenna shown here represents a picocell, and these antennas are separated by 30 meters. RSSI stands for Received Signal Strength Indicator and represents the power of a received signal at the receiving device. We study approaches for localization based on the RSSI values sent from the mobile devices to the base stations for localization. A fingerprinting based method will be used where a database of pairs of locations inside the building and corresponding RSSI values will be first built. During the localization phase, we will estimate a location of a device from the built database. The obtained localization results can be used to study occupants' behavior and their personas. With cellular-based localization, occupants can be tracked over the area of interest. This can allow analyzing occupants' movement and understand their individual as well as emergent behavioral patterns. This can also be used to find areas with high traffic for building retrofitting and future expansion purposes. The data provided by these localization methods can also be used in BIM models for visualization and digital storytelling purposes.
Occupants are one of the leading causes for the differences in predicted and actual energy usage in buildings. The knowledge of how occupants behave and interact within a context is not available to the designers. Such behavior is usually more complex than the assumptions made by the modelers. The modeling and simulation community do not have access to the lived experience of the people due to privacy. Alternatively, IoT allows us to have access to certain information without invading occupants' privacy, example, their current activities or location. For example, in this building model, the person that is far away from the window and on a cooler side may set the thermostat higher than the person on the far left who has more exposure to sunlight. It is crucial to consider the spatial behavior to minimize the gap between the predicted and actual energy use. Such complex analysis are limited in the building performance analysis. We propose personas to better understand and predict occupant behavior and energy usage in buildings. For example, during the design and performance evaluation, the occupants may be assumed as warmer or wearing different types of clothing or exhibiting certain type of behavior. But when the building is occupied, more precise data can be collected from the occupants through localization method. So here's a conceptual model for the design stage. In a building zone, we can define the number of occupants and the type of building, and the component will generate different types of personas that assumes measurable data like location, blind state, or preference data like preferred comfort levels, lighting levels, or proximity. Likewise, personas can be used after the building is occupied by feeding more precise data of the occupants for automation. The measurable data is collected through sensors and localization method. The preference data can be collected from the occupants. This may not be applicable for large space as it is difficult to collect subjective parameters. More precise automation can be used for individual rooms or for regular users. Currently, we have built a component in Rhino Grasshopper to generate personas, and we use energy management system for advanced occupant modeling. It is added as an additional string to the Ladybug Honeybee energy simulation. The goal is to connect the data back for a generative design, and this is under process. Personas may help in understanding occupant behavior in buildings to reduce energy usage.
For this project, we have created a building information model to host all the simulation. The BIM model is the digital campus of Carleton University, and it contains more than 50 buildings, roads, and landscapes. It is an accurate virtual representation of the campus, and it is created to replace the need for a physical scenario. Digital architectural elements can host the sensors, personas, and simulations. And this model can be used to visualize occupancy for campus planning, also for circulation, services, and new building developments, and to simulate the impact of new buildings over existing buildings. For this project, we use the data collected for occupancy, count estimation, and to inform future design. For example, to determine the size of circulation, to select structural elements, or for facility management to operate heating, ventilation, and air conditioner systems. Also, we use this BIM for digital assisted storytelling. The use of digital techniques to create narratives that disseminate information and ideas. Graphical user interfaces were used for visualization of data in real time. And also we use visual programming tools such as Dynamo to link instrumental and architectural representation.